Alright, so this is the first lesson in the flipped classroom, and we're going to be doing this throughout Chapter 4 for trigonometric functions, and the first section is on radian and degree measure. First, I apologize for the audio. I don't have my microphone on me, so it's going to be a little noisy for this one, but hopefully in the future it'll be better. So what we're going to learn how to describe angles, use radian measure, what is radians in the first place, convert between degree measure and radian measure because they're both just ways of measuring angles, and we're going to use these angles to model and solve real-life problems. So let's begin our packet in here. We got a little bit of a history. You can feel free to read through that on your own about what trigonometry is, where it come from. But what we're going to focus on today is what angles are, how to plot them in standard position, and all that stuff. So first, an angle is determined by rotating a ray about its endpoint. Starting position of the ray is called the initial side, and the position after a rotation is called the terminal side. And the endpoint is the vertex of the angle. So we should know all of these terms. You want to get comfortable with all those terms. And also, an angle in standard position, that's what we're going to be using a lot in the next few sections, is when the initial side of the angle coincides with the origin of the xy plane and the positive x-axis. So positive angles are generated when we rotate in a counterclockwise rotation, and negative angles are created when we rotate in a clockwise direction. Let's turn to the next page here, and we'll go through the first example together. You want to sketch a positive angle in standard position below. Okay, so to sketch in standard position, what you want to do is first get your x and y axes. Now, the initial angle is going to be the one on the positive x-axis, so our initial angle is going to be here. And our initial side, our terminal side will be anywhere we want as long as we rotate in a counterclockwise direction. So say right here. And notice I have this little arc here that represents which direction we're actually rotating with this angle. Example 2, same idea, but we want to sketch it in the negative direction. So we still start in the same spot, still on the positive x-axis, but instead of rotating counterclockwise for a negative angle, we rotate clockwise. So maybe somewhere around here. Doesn't matter where you go, again, just indicate that you're actually going clockwise to indicate it's a negative angle. Okay. Next thing we're going to talk about are coterminal angles, and those are angles that just share the same initial and terminal sides. So, for example, let's say we have one angle that is positive, so it rotates in this direction, the counterclockwise direction. But an angle that could be coterminal to this angle could be negative. We could rotate in this way. And if we land in the same spot, even though we went in the negative direction, these angles are still called coterminal angles because the initial side and the terminal side land in the same spot. Okay, moving right along. The measure of an angle is determined by the amount of rotation from the initial side to the terminal side. And typically we measure these angles in degrees. That's what you're all familiar with, but another way to measure these angles is in radians. All right, and let's define what a radian is. A radian is the measure of a central angle theta that intercepts an arc S equal in length to the radius r of the circle. Algebraically, it means theta is equal to the arc length divided by the radius. But it's a little hard to interpret, so let's get a picture for what that actually means. So we want to sketch a diagram representing the definition of a radian. So the definition of a radian will go like this. We have an angle. Okay. Actually, we have a circle. Alright, we have a circle. It's just centered. I'm just centering it on the grid just to be easy to look at. So we have this circle. A radian says, well, this circle has this radius r here, right? So what a radian is we take this radius of the circle and we kind of wrap it around the outside. Okay, so we're going to wrap it around the edge of the circle. And however far it wraps around. So if the radius is 1, this arc length would also be 1. And so what you find is that we create this angle here. And we're going to put a theta there to represent the angle. And theta is equal to 1 radian. Okay, that's because not only does this radius have a distance of r, this arc length has a length of r as well. And so basically a radian is formed by having this sector of the circle where the two straight sides are the radius of the circle, and the curved side is also the same length as the radius. And this theta is defined to be 1 radian. So since the circumference of a circle is 2 pi r units, it follows that the central angle of 1 full revolution corresponds to an arc length of 2 pi r. Therefore, as you're familiar with there being 360 degrees in a full rotation in a circle, 2 pi radians represent 1 full rotation in a circle. So, next example, if there are 2 pi radians in 1 revolution of a circle, how many radians is a right angle? Okay, let's think about this for a second. I'm going to put it on the xy plane again. Now, 2 pi radians, that represents all the way around. We just said it's 1 revolution of the circle, right? So it goes like this. And so if we started here and we went all the way around and ended here again, that's going to be 2 pi radians. All right, that's how far that is. It's 2 pi radians. The question is asking how many radians is a right angle. Well, let's think about this in terms of degrees for a second. If we rotated all the way around a circle, how many degrees would that be? 360 degrees, right? But now we're trying to figure out how many radians is a right angle. Notice a right angle is formed between the x and the y-axis. So if all the way around is 360, and I want to know how many is a right angle. A right angle is just 1/4 of the way around. That's why this right angle has 90 degrees, because all the way around is 360. 1/4 of that is 90. In terms of radians, if 2 pi is all the way around the circle, 1/4 of that would be a measure of 2 pi over 4, which is equal to pi over 2 radians for how many radians are in a right angle. Halfway around, well, all you have to do is 1 full revolution is 2 pi, right? I'm going to draw another picture here. All the way around is 2 pi radians, correct? So if we started here, we went all the way around, it would be 2 pi. This question is saying, how many radians is halfway? Well, if all the way around is 2 pi, take half of that. Halfway around, it's going to be pi radians. Half of 2 pi is pi. And finally, how many radians is 3/4 of the way around? Well, same idea. We have this circle. If we go all the way around from the starting position, it would be 2 pi, or 360 degrees. But the question now is 3/4 of the way. So we want to know how big is that angle there. Well, 3/4 of 2 pi, we can kind of figure that out. 2 pi times 3 over 4. Well, let's write this as a fraction. And to multiply fractions, we do numerator times numerator, denominator times denominator. So we get 6 pi over 4, which both of these are divisible by 2, so we're going to reduce it down to 3 pi over 2. So 3 pi over 2 radians is 3/4 of the way around. Pi radians is halfway around, and pi over 2 radians is 1/4 of the way around. Okay. Sketching and finding coterminal angles. How do we do this? Remember, coterminal angles are angles that just land in the same spot, right? They look exactly the same. Some of them may just rotate around the circle more than once. Other ones may just be negative. What we want to do here is find a positive and negative coterminal angle for theta equaling 7 pi over 6. All right, I'm going to start by sketching 7 pi over 6 radians. Now, I don't know exactly where that is, but I know the initial side is going to be here. And up above, we know halfway around is pi. And 7 pi over 6 is just a little over half. Sorry, it was just a little over pi, right? Because if it was 6 pi over 6, it would be exactly pi, which is halfway around. So 7 pi over 6 is a little bit more than pi, so we're going to be a little bit more than halfway around. So we'll be about here. Now the picture is not strictly necessary for calculating the positive and negative coterminal angles, but sometimes it can be helpful to get a visual of what's going on. I'm going to first find the negative coterminal angle, right? If we went in the positive direction, 7 pi over 6 to get here, we can go in the negative direction and to get here. But the question is, what would theta be? Well, remember, one full revolution around the circle is 2 pi radians. So let's think about it. If we started at 7 pi over 6, and we went one full revolution around, right? If we started here, and we had to go one full revolution around, remember, we're going the negative direction now. So we're taking away 2 pi radians. So to calculate the negative coterminal angle, we're going to start with 7 pi over 6 radians and take away one revolution, which is 2 pi radians. So to answer this question, how do we subtract fractions? Well, we need a common denominator. So this is equivalent to 7 pi over 6 minus, and now I need a denominator of 6, right? So if I multiply this denominator by 6, I have to multiply the numerator by 6. So we're subtracting 12 pi over 6. And 7 pi over 6 minus 12 pi over 6 is going to be negative 5 pi over 6 radians. So that's a negative coterminal angle. To get a positive coterminal angle, we're going to do it the same way. We're going to start at 7 pi over 6, and instead of subtracting a revolution, we're going to add another one, because we want to become more positive here. So to find a positive one, we're going to start at 7 pi over 6 and add 2 pi. But again, when we add fractions, we need a common denominator. So this is equivalent to 7 pi over 6 plus 12 pi over 6, which is 19 pi over 6. So here are here's my positive coterminal angle, and here's my negative coterminal angle. Okay, moving right along. Now we're going to do the same thing, but for degree measure. So let's think about it for a second. If we are finding coterminal angles in radians, we would add 2 pi or subtract 2 pi because that's what one revolution is. Degrees, you should be a little bit more comfortable with this. One full revolution is 360 degrees, right? So if we want to find coterminal angles, we either want to add 360 degrees or subtract 360 degrees until we get one that's positive and until we get one that's negative. So let's start with that 110 degrees, and let's subtract one full revolution to find that negative coterminal angle. We'll find that's negative 250 degrees. Now to find the positive coterminal angle, we're going to do the same thing, but instead of subtracting, we're going to add the 360. So that becomes 470 degrees. Okay, moving right along. Now we're going to talk about a new definition here. Two positive angles, alpha and beta, are complementary if their sum is either pi over 2 radians or 90 degrees. So we might have been familiar with the 90 degrees being complementary, but what's new here is the pi over 2. But remember from earlier, we said a quarter of the way around the circle, a right angle, 90 degrees, is pi over 2 radians. So to find complementary angles, we just have to have their sum be pi over 2 instead of 90 if we're working in radians. Similarly, for supplementary, they just have to add up 2 pi radians or 180 degrees. And don't get too caught up on the Greek. These are just letters like A and B. We just use alpha and beta. Typically, we use Greek letters to represent angles. Okay? So sketch a pair of complementary and another pair of supplementary angles, alpha and beta. Let's start with the complementary angles. So let's start on our xy plane, because we're going to be working with angles in standard position now. So let's say our alpha here is this angle. Where do you think beta would have to be? Remember, they got to add up to 90 degrees, right? Or pi over 2 radians, which means they have to add up to this right angle here. So in order to make these angles complementary, I need beta to be right here, from here to the y-axis, because now if I add up alpha and beta, I get that 90 degrees. Let's do the same for for supplementary. For supplementary, let's start with alpha. I don't have to start in the first quadrant here because 180 degrees is halfway around, right? Pi radians. So let's say alpha is somewhere here. right? Doesn't have to be there. It could be in the first quadrant again. Doesn't matter. Where would beta have to be to make these angles supplementary? Beta is going to be here, because they have to add up to, again, 180 degrees or pi radians. Now, question for you. If alpha is greater than 90, does alpha have a complementary angle? And the answer to that is no. Angles can only be complementary if they're both positive. And if this alpha was greater than 90, I would have to add a negative angle to get their sum to be back to 90. And that's just outside of the definition of complementary. So keep that in mind. If you have a angle that's greater than 90 degrees, you do not have a complement to that angle. Similarly, if you have an angle that's greater than 180 degrees, there is no supplement to that angle. Okay, supplement. If possible, find the complement and supplement of 2 pi over 5 and 144 degrees. Let's start with the complement. We know the sum for two angles, according to up above here, has to be pi over 2 for them to be complementary. So let's start with 2 pi over 5. Let's try to find its complement. In other words, what do I have to add to 2 pi over 5 to get pi over 2? Well, let's solve for x. Subtract 2 pi over 5 from both sides, so x equals pi over 2 minus 2 pi over 5. So this just goes back to getting a common denominator. The greatest common denominator between 2 and 5 is going to be 10. So how do we get our denominator of 10 here? We multiply by 5. So this pi over 2 becomes 5 pi over 10. And to get this denominator to be 10, we've got to multiply by 2. So the 2 pi over 5 becomes 4 pi over 10. So, therefore, the complement to this angle is going to be pi over 10, because 5 pi over 10 minus 4 pi over 10 is 1 pi over 10. So that's the complement, right? So now let's find the supplement for that 2 pi over 5. So what do we have to add to 2 pi over 5 to be the supplement? In other words, we have to add the pi, right? That's from up above. So what are we going to do? Same thing. Subtract the 2 pi over 5, but this time from pi because we want them to be supplementary, not complementary. But this pi is really pi over 1, so we need a common denominator of 5 here. So pi over 1 becomes 5 pi over 5, and this one already got a denominator of 5, so we're good. And when we subtract those two, we find that x equals 3 pi over 5. So this would be the supplement of 2 pi over 5. Let's do the 144. This one should be a little bit easier, so we're more comfortable with degrees. Complement means they add up to 90. But 144 is greater than 90, which means I would have to add a negative angle. And we just stated above that complementary angles cannot be negative. So, for 144 degrees, we don't have a complement. But do we have a supplement? In other words, is there a positive angle that we can add to 144 degrees to get 180 degrees? And yes, we can do that. Subtract 144 from both sides, so we find x degrees is equal to, what, 36? So 36 degrees is going to be the supplement of 144, but there was no complement. All right? So now, you might be asking yourself, what's the way to convert between radians and degrees? Because if they mean both the same thing, they're both measures of angles, maybe I just want to convert to the other one so it's a little bit easier to think about. And you'll find as you get higher up in mathematics that radians is actually the easier one to work with, in my opinion. But either way, if you want to work in degrees, you're going to have to know how to convert them. So let's go ahead and convert this 135 degrees to radians. And we have a little note up here for us. To convert radians to degrees, to convert degrees to radians, we want to multiply however many degrees we have by pi radians over 180 degrees. So let's start with this 135 degrees, multiply it by pi over 180 degrees. Notice the degree units cancel out, so that's why in the end we'll get radians. And we can jump over to our calculator and see what that would be. So I'm going to multiply together this. What do I get? I get 135 pi over 180. But of course, that can be reduced. So we'll do 135 divided by 180 divided by 180. And remember, you can just hit math frac. If you're not sure what 0.75 is as a fraction, just math frac on your graphing calculator and you find it's 3/4. So what we get then is 3 pi over 4, because I didn't type the pi into the calculator, right? I just typed in these two, so I'm just reducing the numbers here, not the pi. So that's in radians. That's 135 degrees in radians. Let's do the other way around. We have radians convert to degrees. The conversion is very similar, but to convert radians to degrees, we're multiplying by 180 degrees over pi. So the fraction is just the reciprocal. So let's start with 9 pi over 2 and multiply by 180 degrees over pi. And we're already in radians, so there's no units there. So our final answer will be in degrees. And notice we have pi divided by pi, so those will divide out. And so we get -9 times 180 all over 2 degrees. And let's go back to our calculators and see what that is. If you want to do mental math, feel free. Be my guest. Times 180 divided by 2. And we'll math frac it. Well, it's already a whole number, actually, so we don't need to. So we just get -810 degrees. Okay, linear and angular speed. For a circle of radius r and a central angle theta, intercepts an arc length of s, given by this formula, where theta is measured in radians. Alright, so let's try an example of applying this. A circle has a radius of 4 inches. Find the length of the arc intercepted by a central angle of 240 degrees. Usually it's helpful to draw a picture. More often than not, that is true. So let's try that. We have a circle with a radius of 4 inches. We want to find the length of an arc intercepted by a central angle of 240 degrees. So 240 is going to be, see, like I'm drawing my axes here so I can get a good measure of where it would be. Well, I know it's 180, that's 270, so we're somewhere between 180 and 270. We're somewhere around here, and this is our angle. And we know that's going to be 240 degrees. So what we're trying to find is the length of this arc here. So I'm going to outline in red. That's the length of the arc that we're trying to find. And we can use this formula up above. S equals r theta. So the length of this arc is equal to the radius of 4 inches times our angle theta. Okay, issue though. Our angle is given in degrees. And the formula says theta has to be in radians. So we have to do a little conversion off to the side first. We have to convert this 240 degrees to radians. So we're going to take 240 degrees, multiply by pi over 180 degrees to convert to radians. And what do we get? Well, 240 pi over 180. And if we reduce that down, 240 divided by 180, we find 1.33. So let's math frac it. And we get 4/3. All right, so we get 4 pi over 3 for our radian measure. So I'm going to put that in our formula. And, well, this is really 4 over 1, right? So 4 times 4 pi is 16 pi over 1 times 3 is 3 inches. And typically in a word problem, we're going to round that answer. So what do we get? 16 pi, 16 pi divided by 3. So we find the arc length is about 16.76 inches. Okay, let's move on. Almost done. It's got two more things, linear speed and angular speed. So, to find the linear speed of some particle, we have to take the arc length that the particle is traveling around and divide it by the time it takes to travel along that arc. We use s for arc length and t for time. Also, to find angular speed, it's very similar, but instead of calculating the arc length divided by the time, we just want to divide the angle at which it rotates through and divide that by time. So linear speed measures how fast a particle moves in a circular fashion, right, how quickly it's moving, while the angular speed tells us how quickly it's rotating. Okay, so let's try this. The second hand of a clock is 10.2 centimeters long. Find the linear speed of the tip of the second hand. Okay, So basically you got this clock, right? I'm not going to draw excess information. We know there's a minute hand, and we know there's a hour hand as well. But this is all about the seconds hand. So I'm going to draw the seconds hand in my clock. And I'm going to put 10.2 for how long the seconds hand is. And what we're trying to find is the linear speed of the tip of the clock right here, the tip of the second hand. So we want to know how quickly is that rotating. Well, not how quickly it's rotating, how quickly is it moving along the outside. And I'm going to use this linear speed calculation here, where we have to take the arc length and divide it by the time. So, how can we figure that out? Well, arc length means the length of the arc that it travels through, right? I don't really have any measurements over here, so the only thing I can really go off of is maybe going all the way around the circle. How long, what's the length of that arc? Well, if we go all the way around the circle, remember, arc length is the radius times the angle. And I know my radius is 10.2, so I can multiply that by the angle in which it rotates through, which is 2 pi in the case of going all the way around the clock. Okay, and so I'm not going to round yet. I'm going to leave this as 20.4 pi. And we have to divide it by the time it takes for it to rotate around. Well, it's a second hand, right? So how long does it take a second hand to go around a clock? 60 seconds, right? So what are we going to do with this s? We're going to divide it by the time it takes. So s over t, in this case, t is 60 seconds. 60 seconds. Oh, and by the way, this 10.2 was in centimeters, right? So I'll put that in there. So the linear speed then is going to be whatever 20.4 pi divided by 60 is, and it'll be in centimeters per second. So let's figure that out. 20.4 divided by, pi, right, divided by 60. Because it's a word problem, so I'm just going to round to the nearest hundredth or so. And so we know that the linear speed is approximately 1.07 centimeters per second. All right? And then last example here. 15-inch diameter tire on a car makes 9.3 revolutions per second. We want to find the angular speed first. So angular speed, if you recall, is just the angle we rotate through divided by time it takes to rotate that angle. Okay, we're given revolutions, right? What's a revolution? A revolution is one way around a circle. Okay, so what angle would it be? Well, let's convert it to radians. If revolutions to radians, how many radians are in one revolution? 2 pi. So our angle here is actually 9.3 revolutions times 2 pi. 2 pi radians per revolution, right? So this will tell us how many radians we're rotating through, and that's what theta has to be in. And how long does it take to rotate these 9.3 revolutions? Well, it says per second, so the time is 1 second. And this will tell us the angular speed. So 9.3 times 2 pi divided by 1, so I'm not going to type that in, but we get approximately 58.43. So 58.43 radians per second. All right, and now the linear speed of the car. Think about this for a second. If we can find the linear speed of a particle going around the tire of a car, that'll tell us how quickly the car is moving, because we're pushing the ground away from us, right, as we rotate that tire, and exactly at the same speed those tires are rotating. Okay, so in other words, we need to do this, linear speed, arc length over time. So what's the length of the arc that it's traveling through? Well, we can talk about one revolution, I suppose. So the arc length, well actually let's talk about 9.3 revolutions, because we already know the angle it rotates through in 1 second from here. So let's use that to calculate the arc length that it goes through in 1 second. And remember, arc length is s equals r theta. So the arc length is going to be 15 times 58.43. That'll tell me how many inches we travel over the course of 1 second. So let's figure that out. 15 times 58.43. We get 876.5 inches per second. Great, so that doesn't really tell us much because it's in inches, and yeah, we would also have to divide this by 1 per second, but we already got that. So we could convert this into miles per hour, make a little more sense. So how would we do that? Well, we're in inches. How do we convert inches to miles? How many inches are in foot? There's 12 inches in a foot, right? So we're going to take this 800, we're going to do some dimensional analysis here. You don't have to do this. If you got here, you're fine. You get credit for that because I didn't specify the units. But if you want miles per hour, let's do that. So it's 876.5, right? We're going to then inches per second. We want miles per hour. So let's cancel out these inches and put it into feet. And then there's 5,280 feet in a mile. 5280 feet in 1 mile. Right? I'm running out of room. I'm going to go on this side. We need to convert the seconds to hours, right? So there's 60 seconds in 1 minute. And in 1 minute and 60 minutes, there is 1 hour. So now all these units cancel out. Minutes, minutes, seconds, seconds, inches, inches, feet, feet, and we're left with miles per hour. So what we need to do is multiply 60 times 60 times 876.5. That's it for the numerator, divided by 12 times 5280 for the denominator. And we find the car is traveling at about 49.8 miles per hour. It's a little easier to comprehend than 876 inches per second. Okay, so that concludes the flipped classroom lesson. We're going to practice the following problems in the next class.